All right, how's it going, everybody? So in this video, I'll be talking about solving equations and inequalities graphically. And this is this is kind of the second part of a little lecture series here. Make sure you watch the first video on solving equations in real life, I think is what I called it, before you watch this one. So we're going to build on that knowledge we learned last time in the previous video. So in the previous video, we talked about how you can use equations and inequalities to compare two different patterns or two different phenomena. So you have two things, and if it's an equation, you want to know when are they equal. If it's an equality, you might want to know when one is larger than the other. So you're able to ask questions. When does this happen, right? When are they equal? When is one larger than the other? This time we want to actually make those questions, which we learned how to describe algebraically last time, at least using function notation, I should say. We want to make that actionable now. So let's say you actually are in a position where you have a model, an algebraic function, say. How can you answer some of those questions? So you've modeled the two patterns and you want to know when they're equal. How can you use technology plus your visual intuition to get the answers? And we'll actually do more with this outside of what's in this video when we look at using Google Sheets to analyze real-world data, which will be an assignment we cover, just not in this video. All right, so the learning targets then, excuse me, the first one, using technology and visual intuition to find solutions to equations and inequalities. In particular, we're going to use like graphing calculator technology. Okay, just so making a graph. And two, comparing equations algebraically and graphically. So you're going to need to be able to like translate between the algebra and the picture. Okay, that's why graphs are so powerful, because they give you a nice visual intuition of something that maybe would be a little more opaque, like the algebra, a little harder to understand. But essentially, I've written the thrust of the main idea here. Algebraically, if you want to find a solution to an equation or an inequality, that's going to show up graphically as where two curves intersect. So we'll see what that means. As a quick recap here, equation means when are two patterns the same. Like usually, often I put in parentheses there what time. That's often the question you're asking. So you're asking, at what time will something equal something else, right? At what time will the stock price equal $100 and I need to sell, right? Inequalities is when is one pattern larger than the other, or conversely, when is one smaller than the other, right? Kind of doesn't matter if you ask, is pattern A larger than pattern B, is the same as asking, is pattern B smaller than pattern A? All right. So if we're going to solve an equation, something that might look like you have two patterns f and g. Each of these patterns depends on the variable on the variable x. So you get an equation, something that looks like f of x equals g of x. And if you're asked to solve this equation, what is it really asking? It's asking you to find the x values where the pattern f is equal to the pattern g. So in other words, what do I have to plug into f and plug into g so that the outputs are exactly equal? So remember, solving equations is like the opposite of plugging in. Instead of knowing what to plug in, I have to figure out what to plug in to make f equal to g. So let's look at an example. Suppose we have an actual function which models each pattern f and g. We'll use a graphing calculator here and our visual intuition to solve that equation. So the equation again, f of x equals g of x, and now suppose we're given two models, okay? So I get a couple of quadratic models here. So how am I going to do this? Okay, it turns out to be really quite simple, right? So I have two sides of an equation, a left side and a right side. Each side is its own pattern, right? And here I see the two algebraic forms of the pattern, the functions, 2x squared minus 4 and minus x squared plus 7. So what I could do is I could say, well, let me look at each of them separately and graph each side of the equation. And then all I have to do is see where do the two graphs touch. And it's literally as easy as that. So here are your steps, right? Graph each side of the equation separately. And then the second step, see where the two curves touch. Where two curves touch are called intersection points. That's the fancy, formal, mathy name of these things. But the intersection points are going to give you the solutions. So I have these two functions here. I want to know when they're equal. Let me just pop up, and I'm going to go to Desmos to do this. So the first one was f of x equals, what was it, 2x squared minus 4. And notice Desmos, I pop in f of x equals 2x squared minus 4, and Desmos gives me this nice red curve. And the second one, g of x, is negative x squared plus 7. So I'm just going to type in g of x equals negative x squared plus 7. And I get this nice blue curve. And notice that there are 2 points exactly, and Desmos almost like highlights the 2 points. See, it shows me like clearly it makes these 2 little intersection points. That's where the 2 curves are equal. And so if you're asking when does the pattern f equal the pattern g, when does the left side of the equation equal the right side of the equation? Well, if you graph each side separately, then you're just asking, well, when do these 2 curves touch, right? And so Desmos is so nice that it'll literally you just scroll your mouse over it and it shows you what the solutions are. So in other words, I have 2 different solutions. There's 2 times at which the red curve and the blue curve are touching, right? The inputs, the x values, are negative 1.915 is one of the x values, and the other one is positive 1.915. This is nice and symmetric, right? So if I go left 1.915 units, or if I go right 1.915 units, in each case, the 2 curves are coincidental, so they're touching, right? Okay, so it's that easy to solve an equation when you have the model using technology, and you get a nice visual intuition too. Okay, so there are the steps again, and solving the equation, we get 2 solutions. The x, what you have to plug in, was negative 1.975 for the solution on the left, and positive 1.975 for the solution on the right, the intersection point on the right side of the graph. I also recorded the y values, the outputs. They were both at 3.3 repeating. Okay, so that means when you plug in x equals negative 1.975, f gives you out 3.3 repeating, and so does g. Or if you plug in the positive 1.975 to x and g, you get out 3.3 repeating. All right, so suppose now, same sort of thing. Instead of asking when are the 2 patterns equal, you ask when is one larger than the other. So in this case, find the x values where f, the pattern on the left, is less than g, the pattern on the right. And with a graphing calculator, it's really quite easy. So this is, let's say I use the same exact functions. Okay, so instead of doing equality, I'm going to do inequality now. But you can do the same thing. Graph the left side of the inequality. Graph the right side of the inequality. It's going to give you 2 curves. And then just see where is the left curve smaller than the right curve. So since I already have that pulled up, it's pretty simple to do. F is in red. That's the left side, right? Maybe I should have called it like left of x. Well, let me do that. Oh, it didn't like left of x. Too bad. Okay, I won't do that. But it's like f is the left side of the equation and g is the right side of the equation. So I graphed them separately. Now, where is the left side smaller than the right side? That was my equation. Where is f, the left, less than g, the right, or red? Where is red less than blue? Okay. Well, all I have to do is say, okay, for which values is the blue curve on top of the red curve? And notice that the intersection points play a role here again, because the intersection points actually split, since it's where they're equal, they're going to split up the regions into where they're not equal, right? So the equality, the points where they're equal, splits up where they're not equal. In other words, this one is as easy as saying, well, the red curve is less than the blue curve as long as you're in between the 2 intersection points. And I just have to look in between them. Every time I'm there, red is below blue. If I'm if I'm to the left of this one, of this intersection point here, then the red is on top of the blue, right? So red is larger than blue. If I'm on the right side of this one over here, then again, red is on top of blue. So all my solutions to the inequality, f is less than g, the red is less than the blue, occur in between the 2 solution points. And that's really all you have to do. So the solution in words f of x is less than g of x whenever x is in between the two intersection points. And if you wanted to write that in numbers, I think I really believe it's very helpful to write things down just in plain English. If you can understand the concept before you move to the numbers, I think it's very helpful. It'll kind of help you tease out. So how could I write this using inequalities and numbers? Well, you just say f is less than g whenever either x is larger than negative 1.975 and x is less than positive 1.975. In other words, all x values that are in between, remember negative 1.975 is the left side, the left intersection point, 1.975 is the x value of the right one. So as long as we're bigger than the one on the left and smaller than the one on the right, then we're good. So in other words, this is saying this part on the left is saying x is not too small. It has to be bigger than the left intersection point. And the thing on the right over here is saying x has to be less than 1.975. X can't be too big. It can't be bigger than the intersection point on the right. Okay? And so just to kind of summarize that, the intersection points not only tell you where the two functions are equal, they also separate the regions where they're not equal. So I have like something that could go on an inspirational poster or something. To solve inequality, start by finding the equality, because the equality where they're equal is going to tell you, it's going to split up the regions into where they're not equal. And then you just have to compare which function is bigger if you're on each of those regions if you're solving an inequality. Okay. Here are the steps, and that's pretty much all we have for this video. So if you have to solve an inequality graphically, start by graphing each side of the equation. Sorry, that should say of the inequality. Step 2, look at which function is larger in each region. So you're going to look around the intersection points and see which function is bigger in each region. And then just identify those regions. Just look at the graph and see which is bigger. And you'll have to ask yourself, is x less than some number? Is x bigger than some number? But if you just carefully go through, you'll be able to pick off those regions. All right, so in summary, when you're actually given a function, you can solve an equation by graphing each side separately. The intersection points on the graph, that is where the two curves are touching, are intersecting, is where the two functions are equal. And that's exactly what you're asking when you're asked to solve an equation. And then finally, we talked about how when you're looking at inequalities, the intersection points also mark the boundaries between each of the regions where one is larger than the less. So they mark the boundaries between the solutions of the inequality. All right, thanks for listening.